independent living, continuing care community. So, and I'm in the process of getting an observatory built here. So that's been pretty exciting.
Are you building it yourself, or are you having the community do it?
Well, both. I'm sort of taking the lead on it as a resident.
Okay.
I'm working with the staff, and they just laid the slab for it, for the building. We're gonna have a small, we're gonna have one of the next dome observatories, a small observatory, but I'll have my 11-inch scope in there, and we'll have it all permanently aligned. So yeah, there it is.
Okay.
That's actually Bruce's
8-inch.
No, 11-inch.
that I took. Hold on just a minute.
It's an 8-inch.
That's Bruce's old 8-inch scope that I actually photographed the conjunction with.
Oh,
So,
okay.
on the slab. This right here is the AC power coming in.
Okay.
But
How'd you end up with Bruce's 8-inch? I thought you gave him your 11-inch.
yeah, he got my 11-inch, and then I guess he was overcome with gratitude, gave me one of his 8-inches.
Okay.
So he did. He just asked me if I wanted one of them, and I said, yeah. This is a vintage 1975 year scope.
Yeah, those are good scopes.
Yeah, works great. So
you're in a similar situation to Mike Chibnik there.
Yes, and I have a next dome.
He moved up to Rio Vista, and he fell in with a bunch of gullible retired people, and he's got them all building an observatory up there.
where is this? I didn't hear.
Rio Vista. Rio Vista, it's Sacramento River Delta.
Yes, yeah, I know where Rio Vista is. Yeah, yeah. So anyway, I'm hoping we'll have this up and running first part of this next year.
Oh, that's good to hear. Yeah.
My fingers crossed.
The one thing you have to be careful about with the next dome, because I got one, is sealing of the door. You have to make sure that the walls are circular enough. I didn't do it to mine, and so there's a gap at the top of the door that I have to monkey around with. So just be careful with it. Other than that, it's survived major winds like nobody's business. And in Rio Vista, it's not uncommon to have 30 to 50 mile an hour winds. So it's held up pretty good.
So I want to remind everybody that there's two different views. You can go gallery view or speaker view in the upper right-hand corner of your screen. And it's kind of nice if someone's trying to show you something to have speaker view come on, then you could get a bigger view of what the person's holding in their hands, perhaps. So that's the one advantage. And it makes you focus on that one person, I suppose, instead of everybody else. But it's good to see everybody at the moment, all 10 of us at the moment. Henk is on twice for some reason. So I'm thinking, Mike, did you want to try to carry on from last week and do your little presentation?
Okay. So let me start off by saying what we started out with was the superhighway that they've been talking about, that follows what they call space manifolds, which is just nothing more than a mathematical name for a three-dimensional curve of whatever you're measuring or doing. And so, and then we talked about the fast Lyapunov indicator, which is what they used to determine where the superhighways were. And we started in with a guy named Lagrange, who laid the foundations of the superhighway, and more importantly, a thing called the Larangian orbital points, which a lot of spacecraft is making use of, and no doubt the new super duper whiz bang Webb telescope is going to be parked in. A whole second. I need to go do a share, don't I?
Right, share your screen there.
Okay. Okay. So,
I have Mike, I got another question for you. That you pronounce his name Larange. I would always thought it was Lagrange or something.
It's Lagrange. I just screwed up. That's all. Okay. So can you see my
PowerPoint? Yeah.
Okay. So anyway, 1700, he was probably one of two major scientists other than Messier that survived before, during, and after the revolution, and survived into, well, this guy didn't survive into the next monarchy, but he was pretty well thought of and left alone. So the Lagrangian points, there's 5 of them, of which if we're talking about Jupiter, the L4 and the L5 are the Trojan asteroids. But the Earth has also objects that are in the L4 and L5 points also. And also we're now having a lot of spacecraft that are hunkering down in Lagrangian point, which allows them to be away from the Earth, away from light pollution and RF and other things, and stay pretty close while being far enough away to do their jobs. And so this is a sort of a diagram showing the equal, I believe it's the gravitational potentials. It's like an elevation point. And the reason why I show this here is that the 2 green dots over here, L1 and L2, show the points where when you start placing objects, they'll have a tendency to not move away from here. They're relatively stable. And so at this point at the L1, you'll notice that the curve goes in and around, comes around and goes in and out. Whoops. Okay, so this is a stable point. This is a stable point. And you notice that this seems to be of a not so well-defined well, you might say, of the 4 and the 5. And kind of interesting, there's a point on the opposite side, L3, which is another gravitational well, but I'm not sure how strong it is compared to the other 2. So the L4 and L5 lie at 60 degrees to Jupiter's orbits. That's where the Trojan asteroids are. Were discovered about 100 or 200 years ago. And when they ran the Linapov indicator, it predicted that's where the Trojans would be. So again, back to last week, this is sort of like, it's nice to have a model and have actual data that predicts, actually, I should say, confirms your predictions. Okay, it's less of a theory and starts becoming more of a law. So this is sort of the software that I use for my MESO 200, and all these green dots are asteroids. And this one right over here is, and I can't see this here, hold a second here, 624 Hektor, which was discovered in 1907. That is a Trojan asteroid, and you can image that. So that's one. I give it a pretty good chance that quite a few of these other ones are also Trojan asteroids. And this is 60 degrees approximately away from Jupiter. So tonight, when Jupiter's down, and the great square of Pegasus is up, this is where you're likely to see the Trojan asteroids. Of course, the other Trojan asteroids, which they tend to call the Greeks, are on the other side of Jupiter, and so would be up in the early morning sky. And so
Would that appear kind of stationary because it's at the Lagrange point, or does it move around?
no, it's more or less stationary with Jupiter. So if you could see things slow, speed things up, this would move exactly the same point as Jupiter.
Oh,
But there's another one that's much more local. I mean, the Lagrange point is actually something that's pretty universal. It happens more often than you think, because I was thinking of, oh, why can't the Earth has it? Why can't the Moon has it? Well, the Moon does. And so this is not a funny story, but an interesting story. About yesterday, I decided to go through all my magazines and start ripping out articles and making more room for more magazines, and started sorting things. And I came across this article from Sky Telescope this year in January called and I'm not going to pronounce it, the K clouds, okay? These clouds are clouds of objects, and I'll put the quotation marks objects with respect to the Moon. And they move, and they've been verified to move exactly in synchronous to the Moon, but are at the Lagrange points. And so they're called that wonderful name because Casimir is a guy is Polish. I can't pronounce Polish. In 1951, began to search for these objects, and he used 8-inch refractor and 24-inch reflector, and for many years he couldn't find it. And then a friend of his, Witkowski, suggested that don't expect something big. Don't expect a big rock that's going to show a lot of light, going to be a pinpoint. It's probably going to be something much smaller because the gravitational field of the Moon is much less. Start looking for something like dust. And so when you think about it, there's another object that many of us know that's made out of dust, that's pretty faint, that's pretty large, that if we're lucky, if we have clear skies, we can see. It's called the Gegenschein. Okay. And so in 1956, he went to Scanlati Pelso Observatory and saw the doggone things with his own eyes, okay, as a rather nebulous, very faint cloud. So he had that aha moment, and then he was the first to record it on film, using a regular Leica camera with a normal lens, going for 11 to 15 minutes exposures. Now, the only reason why he was able to see these is because he had clear and dark skies. And so just like the Gegenschein, you need pristine skies that are very dark in order to see it. But I guess you can see it. And so the size of these is about between, found to be about 2 to 3 degrees. And I guess at the time, it was 2 clouds and 8 degrees. And again, he looked after the Moon was below. Now, one thing to note, the article says that these clouds are not very well defined, and they're kind of transitory. Other things can affect them. And so, but what happens is that they get replenished all the time. So the size and the shape can vary from time to time. And basically, this is on the right there, shows sort of like a map of the brightening, where he decided that that's where the clouds were. two small clouds. So this is sort of like a diagram of a certain amount of brightening towards, and I guess he found it in Leo at the time. So again, this year, they're just on the left, they're just showing you how, the mathematics or the geometry of the moon with respect to its own L1, L5 points. So I suppose it's possible that in the future, that for monitoring the moon, or for, let's just say, you want to have something that's not affected by the moon, you could have it at the L2 point with respect to the moon, some sort of spacecraft observatory. And so I was thinking about this yesterday, and I'm thinking there's got to be other similar things happening in the universe like this. It just doesn't happen with the stars. And so I'm thinking that in the future, if we have telescopes that are sensitive enough, and they'd have to be very sensitive because these clouds are, when you think about it, the Trojan satellites and and especially the W clouds, they're extremely faint. They're going to be in multiple star systems. Okay, it could be that they're made up of larger material just because the gravitational workings is much bigger. It's entirely possible that, like in a globular star cluster or something like that, where you got stars whizzing by each other pretty closely, that you might not have orbiting systems as much as you would have stuff in the Lagrange points, for all we know. It's entirely possible. And also, you could probably take it one step further, that in our galaxy, where we have large clumps of objects and matter and stuff like that, there might be a form of structure that is similar to Lagrange points, and even possibly further along bridges between galaxies, such as this here. This is the bridge in the Magellanic Cloud, and with a bunch of other galaxies that they're orbiting each other in a stable enough manner, which could be possible. You might have points where stars or matter or whatever is in a Lagrange point and has its own little neighborhood, you might say. That's one thing the science writers haven't done, but maybe I took it to the absurd, but I think it's entirely possible somewhere that could happen. So again, superstring. One of the things I want to share with you is an interesting website, hyperphysics.phys. This here, just go hyperphysics. This is a very interesting site. It's got a lot of different subjects of physics, as you can see: mechanics, electricity, vision, astrophysics. And so it goes through the mathematics and some of the explanations. So if you have a hunkering, if CNN or Fox News is getting kind of boring to you, you may want to get yourself and, look at this here. I spent half a day going through this here, going, oh, yeah, I remember seeing this in school, and then you start digging deeper into it. So it's an interesting place. So that's it. I'll do a stop share.
Thank you, Mike. That was great.
I gotta.
No.
Yeah. Okay.
Yeah, thanks.
Thanks,
Hektor
Mike.
rang a bell. I got a positive occultation on Hektor back at the end of October.
Oh.
How bright was it?
Well, It was, I can't remember if this was a star brighter or asteroid brighter. I think it was star brighter, judging from the light curve I got, it showed a pretty good dip. But here's the trace. Let me do screen share here. Here's a trace they did relative to the a Dammit model they had, which is a model based on light curve variations, to try to get a shape.
Okay.
So I'm the little green curve, green line at the bottom there. So I had a
Well,
short.
you just made it. You just made it.
Just made it, just barely, yeah.
I thought the model was named after you missed it.
Yeah. Oh, damn it. It's not a, it's the guy just does a rough fit here. It's not a really
Yeah, I understand.
rigorous fit. You can see it says no reliable position or size, but anyway, it was fun to hear Hektor again.
Yeah. Huh.
Any other comments on Mike's program there, Lagrange?
I think that the Lagrange stuff can certainly happen on a bigger scale, but some of the pictures you showed were of galaxies in active collision with each other.
Yeah, I know.
To each other. And they've, as you pointed out, they've got to be orbiting each other. And I assume they've got to be orbiting each other for several revolutions to get these things built up and trapped.
Right. For a long time.
Very, very long times.
Yeah. But if you, I just saw a simulation on how the Milky Way formed, okay? And there were times when things kept going around each other before something got dragged in or something like that. Yeah, it's like I said, it's probably pretty unlikely, but if,
it's a good thought. It's good to reach out there and think out of the box like that. Good job.
Okay.
Yeah, I looked up today, actually in past days too, they have kind of an interesting multiple videos on the life of Lagrange on YouTube, which is kind of interesting, just a history with Euler and all those guys, how he got brought in. And then on Wikipedia, they've got some interesting information on the Lagrange points, Sun, Earth, Earth, Moon, Sun, Venus, Sun, Jupiter. I guess one of Jupiter's moons, I think, is stuck at one of the Lagrange points. So, and then you think, you like the one you talked about, the lunar one on the far side, you think, oh yeah, that'd be interesting. But then the problem, and the same on the other side of the sun, but the problem becomes communication with the Earth. How do you get signals? You have to have something in between. But
there are plans to build a communication infrastructure around both Mars and the Moon, so that if you put a satellite anywhere around that or a station anywhere on either body, you're always in communication with Earth through this sort of GPS system.
And the Japanese had I'm sorry, the Chinese with that Chang'e 5, they had an orbiter that they relayed to talk to. I'm sorry, Chang'e 4, the one that went on the far side.
Yeah.
So they had to have a relay.
Yeah.
Yeah.
In terms of Lagrange, there's a story I had heard about him and Napoleon, because he was asked he got so famous, he was asked to give a discussion or a lecture to Napoleon. And it turns out that Napoleon is the 200-year ago equivalent of a fundamentalist Christian. And Lagrange is not terribly a Christian. And so when he explained the orbits and his mathematics and that all, at the end, Napoleon was said to remark that he didn't see any inclusion of the deity in this. And Lagrange thought for a while, and he says, I'm sorry, I just didn't see any need to put him in. And everybody in the room thought this was a career change or a career statement on Lagrange's part, but apparently he got away with it. So.
Yeah, that's like
he didn't say that.
Bob, I think you're muted yourself, but it's been a debate between science and religion since.
He didn't say there wasn't a God. He just doesn't say that God was probably important in the discussion he was talking about.
I think he was careful not to say that. He said
he was a bright guy, not just in mathematics.
Yeah.
I read that same story.
Oh, you did? Okay.
With Stephen Hawking, that was the same thing. I think like the Vatican was okay with like a trillionth of a second after the Big Bang, but they said, you know, in terms of religion, you know, it's like you have to say God created the universe. So they didn't like the idea of the Big Bang, you know.
Well, let's see. Dobson used to tell everybody that God made hydrogen, and then hydrogen made everything else. I think that's what he used to say all the time.
Yeah, that's the latest comment in religious circles regarding evolution. Is that supposedly God created the heaven and the earth and all the animals in it and all the plants, but evolution is how he did it.
Yeah, starting 6,000 years ago, right?
Yeah, there's no conflict.
You're talking about being able to navigate the a very uncertain time, and of course, for those who didn't hear it, he said, "I believe that in general, one of the first principles of every wise man is to conform strictly to the laws of the country in which he's living, even when they are unreasonable." That's what he said.
That's the Bible path.
Very smart. So Henk had something a few items that he wanted to talk about this evening. But before we do that, I just want to recognize Bob Richard, the first time showing up here tonight.
Yeah, hi, Bob.
The blue checkered shirt there.
Hey, Chuck. Hi, Chuck.
Bob was a long time SBAU member. And down below, we just had Chris show up, Chris Olivo from
Hi, Chris.
Hello, guys.
Welcome
City
back.
College teacher, an art teacher at City College still, right?
Yeah, and I mailed in my membership. I promise.
Okay. Good, we can use the money.
And I don't think anybody else needs to be introduced. I think we're fine. So Henk, did you want to present something?
Hank, how come you have two screens open?
Well, the thing is, I've got my stuff on my laptop, all my Astro stuff, and
Oh, that's right. You've got two sources. Okay.
yeah, and for chatting with the video, the Galaxy Tab A is just superior. It's just so nice to use. So, but I don't want to have to copy everything over, and I've got different programs on different platforms because one is an Android, the other one is Windows. So anyway, I'll just try to share. Let me just start with this, trying to share here, and this is the first time I'm using Zoom on Windows. So let me see if I can even bring the window up. So I'm going to try to share a window here, and I can't even find my Zoom. I see a video. Oh, yeah, okay, yeah. I see
Now,
myself
you
now.
guys notice that Chuck has got himself muted, so you could mute yourself if you're afraid that some sound might come through from your home that you don't want coming through. So you can always consider doing that if you think there's too much noise in the background or something going on.
Okay, I'm sharing my screen now.
Yep, it's working.
Yeah.
Good.
Yeah,
Okay.
you got it.
Okay, so what I want to talk about, this is about a discussion that I had or that somebody started on the sky searches. I don't know if you guys heard of the astronomy forum. Okay, so I've been on the astronomy forum for quite a few years, and the manager just didn't do it anymore. The servers went down and whatever, and it's now called the sky searches. So I can recommend that forum. But there was somebody on there who started a discussion about an artificial star. And I've been trying that myself one time with a doorknob and trying to light it with a little laser pen and so on. And anyway, it didn't really work out very well. But there was a discussion, okay, if you have an artificial star, just how far away do you have to put it from your telescope? And what is the size of the hole that you need to have in order to see an airy disk pattern if you want to test your telescope with that? And well, I didn't respond very much in the beginning, but and at first I thought, well, this is probably a very simple explanation. Like if you have a point source very far away, then you want the wavefront that enters the telescope to be as flat as possible. But if you do the math based on that, then you end up with distances that can easily be 1,000,000 kilometers. So that's not the right method. And I started looking at an article by Niels Olaf Carlin. I don't know if you guys heard of that name. He is from Cloud, I believe. Sorry?
Yeah, I have.
Yeah, he's a cool guy. He passed away a couple of years ago, but he did a lot of work with Dobsonians, and he did some math stuff and so on. And he's got a very nice homepage, which I have here somewhere.
Hey, Hank, can you repeat that name, Hank? The guy's name you just said?
Yeah, Niels Olaf Karlin, Nils, and then Olaf Karlin.
He
He's
designed my telescope with his mirror cell.
Oh, okay. So his claim to fame is also the bar-load laser. A lot of people are doing that now. So if you bar-low it, you get a little cloud around the donut, and it cuts the error in half, supposedly. Actually, I have one of those myself because I've got a Howie Gladder, which has that built in. Anyway, yeah, and he was a prominent figure on the Equatorial Platforms Yahoo group. I joined him there for a while as well because I was into equatorial platforms and will be again someday, I think. Anyway, so I sort of know him. He had an article where he sort of described, and I'll pull that up here. I've got the link open somewhere. So yeah, this is the link. And he describes the shape of the mirror over there to the left, and R is the radius. It's a parabolic mirror, offset, and so he put it in the context of testing for. So the thing is, the difference with the story that you usually hear, that all bundles with a parabolic reflector get focused in one point if it's parallel to the axis and if the light comes from infinity. The thing is, if you put the light source not at infinity, then that does not hold anymore, and a telescope is not a perfect lens. In other words, the rays will not focus in one point. It will be spread out. So the whole math becomes a bit different, and that can wreak havoc on your airy disk pattern. So I think he used the lens equation. So that's what you see here. This follows straight from the, can you see that highlighted in blue?
Mm-hmm.
That's basically the lens equation that you get. 1 over A, 1 over B is 2 over R. But I'm not sure if that even holds. I decided to just do the math just based on geometry, because this is a parabolic surface. And if a ray comes in from B and hits the mirror over there, then it's just a matter of computing the tangent over here, and then the normal, and then flipping it to the other side and drawing it to A. And we should be able to figure that out, right? So I got intrigued by that and started looking at it. So that's how I started. Here's a figure that describes the basic situation. So the light starts at B. So if you do knife edge testing or Foucault testing, then you would put the light source somewhere inside the radius of curvature, right? And it gets reflected by the parabolic surface. If you can see that, x equals y squared over 2r, and goes to the knife edge A, that would be. Or you could have your artificial star at A, and the light would go the other way and would focus here, or focus approximately. Anyway, so my first task was, okay, if the light source is at B, where would it cross the x-axis? Can I figure that out? So this is a complex figure, but all these things are in there for a reason. So it helps to, it helps the math. It wasn't too hard to figure it out. It's just putting a few things together, and I'll just skip all the math. But the solution is this equation here. That is, I believe, yeah. So that point A, if you go back to the figure here, that's A is A comma 0, that little a is given by this equation. So if B is where you start the source. So it's a fairly simple relationship. It's not necessary to come up with a closed formula, because if you wanted to do anything, you'd have to do it in a computer anyway, and you can use simpler equations to do it right. And I actually used that to verify this analytic expression. I ran it through Scilab, and here's an example of what you can get in Scilab. So this is a case where I put the source at 1 meter away. It's an unrealistic case. The radius of curvature is 0.2. And of course, it's a parabolic mirror, so there's not really a radius of curvature, but it's the constant R that describes the curvature of the mirror, right? So what you see here, in blue lines, you see the light coming in. Each blue line is a ray coming in from the right. this red line here is the tangent to the telescope. So it gets reflected at an equal angle down to this point here. And what you see there indeed is that the light does not focus at one point. So it's spread out. And well, that formula that I had earlier that describes exactly where B. So that formula can be applied if the light comes in from the right or from the inside. Doesn't matter. It's really symmetric. If you solve the problem from one side, then you can flip A and B and you've got the solution to the other side as well. So I'm just going to say that the math is correct. I verified it in MATLAB. It's all hunky dory. So I thought it looked kind of interesting. And you can also see that the light rays or the perpendiculars to the tangent here, they start moving away from the center. So the focal point here for the ones that are close to the x-axis is about here. And the further away you get to the edge of the mirror, the further away this quadratic profile pushes that point out. You will not see it with a
yeah, the rays at the center of that hit toward the center are hitting a more spherical surface.
Yes.
The real parabolic difference
Right.
are farther out. So you're getting more close to the ideal case when you get toward the center.
Yeah. So let's see, go back to the figure. So the next task was, okay, what is the path length if you put a light source at A and it gets reflected by the mirror and hits at B? Because that's what matters for interference and for an airy disk. So the difference in the number of wavelengths is going to be critical for the airy disk. So I did that math, but it's actually the wrong question. But anyway, I can tell you that that's the next part of the story. It's a dumb idea to do that, but I did it anyway. And I did it for two cases where A is the source and B is the target. It ends up being a symmetric solution as well. So you can interchange A and B, and I wouldn't have had to do it twice. The thing is, it's probably a useless problem, because if you look at the figure that I had earlier, let me see here, this guy here, you can tell that so these are where the line stops, that's the the total line length is fixed, and you can tell that these lines, for the further away you go from the center of the mirror, really fan out, and there's no the question of whether that endpoint interferes with any of the other is that rather irrelevant. They're just too far away from each other. It's not the right question to ask. You have to really check where these light bundles are the closest, and that's probably where you'll find interference. It's a difficult question. I don't know exactly how that works. If you have light rays that have waves on them, okay, and they don't intersect in the right point, they are close, because in this case there's not one focal point where they all come together, right? So there are some that intersect in one place, and others intersect in a different place. So just exactly how does it work out in terms of interference? And is there a thing like, okay, if two of these rays are close enough, is there some law of physics that tells you whether interference will happen or not? That's something I'm not familiar with. I just do the geometric part. So I'll leave that question aside. But it seems like if you zoom in, because I've got better pictures here, this is a case where I have my, let's see, this is also a fairly unrealistic case. It's a lot of curvature, but it does illustrate the point. I sent 200 rays here, and you can see some dots in the middle. So if we zoom in to that area, then what you see here looks like this. So these black markers indicate, they correspond with the total path length that corresponds with the nominal path length for the ray that goes through the x-axis. If you do the math and calculate, if you go from A and then it gets reflected into B, then you will end up here, and all the other ones have an equal length as that one. And so you can tell for the rays that are further out, they are fanning out towards the right. And there's the way these reflections work, that they sort of the ones on the outside, they are very far away, and they converge on the x-axis much farther away. And that's why I'm saying, the intersection with the x-axis is not really the right problem. You probably have to find an area where all these bundles are just closest together, and then sort of figure out what the width is, and based on that, assuming, you know, then you have a measure for the number of wavelengths that fit in there. So the red dots that you see here are actually the result of doing an optimization where I define as a cost criterion the distance from the top ray to the bottom ray and try to minimize that. So I try to find the point where these rays in a vertical sense are squeezed down. If you find that point, then the horizontal distance between those points are also automatically get smaller as compared to this hyperbolic sequence of black markers over there. That's much further apart. And so that's the distance that I've taken a look at and compared that with the wavelength of visible light and see how many wavelengths that is. So I did it for a couple of examples. So this is actually, this one corresponds with my own telescope. It's a 12-inch with a wavelength of focal length of 1500 millimeter. And I've put the rays at 120 meters distance, the artificial star at 120 meter distance. That seems to correspond with other values that I see here. And I've got a table where I've got 4 scopes. So number 1 is my own scope, and with the 1500 focal length, the source is 120 meters, and the peak to value.
You just chose 120 meters?
I tried a number of values. I think that paper of Niels Olaf Carling also mentioned the number 120 for a 12-inch somewhere, I believe. So I picked that number and I get a distance horizontal width of all these markers of 416 nanometers. So that's like violet light. So 1 wavelength of violet light would be in there. And the peak to value is sort of like a worst case value. It goes from, you know, it's one extreme minus the other. So in practice, it's going to be, the effective width is going to be a little bit shorter, I think, for your interference pattern. So now, of course, that's a whole wavelength, and you don't want a whole wavelength because that would, you know, cancel out. But it looks like roughly that might be what we're shooting for. And I compared this with values that Niels Olaf Carling had. He had a 6-inch mirror with a focal length of 912. And he put it at 12 meters, and he got, and I get 853 nanometers. And I have to say, okay, so the difference with what I do here and what Olaf Carling did is that I'm not using lens formulas. I'm just going from basic geometric equations. I follow every single ray and see where it goes. And I believe that should be pretty exact. Whereas I believe if you use the lens formula, you're not exact anymore. So I believe
the lens formula is only for an ideal lens or mirror.
Yes, exactly.
Does not tolerate any aberrations.
Yes, and that one equation that we were talking about, that's 1 over A plus 1 over B is 2 over R. That will not hold with the results that I get. It will be, but I claim that mine is exact, and so it does not follow the ideal lens equation. Anyway, going back to oh yeah, so let me just see what he had for that particular case. He mentioned okay, so 6-inch mirror f6 D152. He had, okay, A is 9,000. Okay, what P wave? Let's see here. Okay, P 560 nanometers and wavelength of a quarter. So he claims a quarter wave at a wavelength of 560 nanometers. He has to put it 9 meters away. Well, his numbers are different than mine, and
So Henk, what is the light source that you're talking about?
the light source is not specified here. This is just a geometric, you know, investigation.
Okay.
But it would be, I think he was looking at 560 nanometers, right? That's what is that? Red light or something?
That's
red
almost,
laser.
I don't know if that's red. That's close. That's close
Yeah,
to
green
wider,
maybe.
yeah.
Could be a green laser, whatever.
He's looking at a point source that's on his axis. And
Yes, exactly. So it's whatever you would use for an artificial star, which would probably be monochromatic light, if you want good results, I guess. I don't know what kind of things artificial stars use. I believe I've seen some with white light, right?
Well, we do it, and when we test our mirrors, we do it with pinholes or a small LED.
Green LED.
Give a little bit of an extended object, but a good way to do it, the way we used to do it back in the 60s, was to use a small ball bearing and shine a bright light onto the ball bearing.
Oh.
Yeah.
I've got an artificial star that's a tiny pinhole in a metal aperture, and behind it is a bright white LED.
Okay.
Yeah. You know, the way they test mirrors is not by using artificial stars, but what they do, if you have like a 12-inch mirror, then they get another 12-inch mirror, point it face to face, and they put a pinhole at the focal point behind the eyepiece and shine a laser light on it. So the light bundle that comes out of that telescope is parallel. It's exactly like a star, and it hits the other one, and you can test the other one with it. That's how professional telescope.
Well, where I worked, we used a what is that called? Oh geez, what is the thing that detects the gravitational waves? That's a
Interferometer?
Yeah, we used an interferometer, and then we got lines across the mirror, and then we would go through a computer program to analyze the lines, and it would map the surface of the mirror for us.
Yeah.
We had to do years ago, had to do a line of sight calibration in a lab. So we designed a box that was like 3 or 4 feet square with black plexiglass, and then had some precision mechanics place drill holes according to a star map that we had. And then actually I went out to Radio Shack, and we put LED lights into the little holes, and just in the lab, it was we didn't have that much space, but about maybe 30 feet, 35 feet or something. We pointed a sensor at that, and it kind of worked, you know, it sort of worked. We had to make them really precise. We knew there was going to be some distortion and stuff, but
it depends upon what you want to use it for, right? I mean,
yeah,
the goal of this thing is to be able to see an airy disk, so that does require a high quality artificial star and a long distance. If you just want an artificial star, like I did some stuff with an artificial star just to test auto guiding with, you know, so
I've seen some stuff online with that. Yeah, they just point a laser at a wall or something like that.
Exactly. I had like a Christmas glass ornament of a Christmas tree, a ball that I put over there in the corner, and then I was shining a light at it. I set the tracking in my mount for guiding to a factor 0, something like that, and then so it doesn't expect that it tracks the sky, or I turn the tracking off, and then I was able to move the ball a little bit and see if the guide scope, the scope system would actually follow it. So that's kind of
Bob, what were you making those artificial constellation plates for?
Oh, we had 2 or 3 different projects for these experimental satellites that were going to be launched, just a one-shot deal. And we had about 5 different algorithmic things that was going to test. And the first one was line of sight calibration, and it couldn't do this thing, you know, since I got into astronomy, this plate solving, we didn't call it plate solving. We just called it like lost in space or whatever, but it couldn't do that. But if you got rough, you know, RA deck coordinates of where your sensor is pointing, it could zero in on it by just doing every star that was in its field of view. It would form a triangle and just form triplets, and then it would solve the triplet problem of like, where am I actually pointing? And I was one who's supposed to write the software. I sort of inherited it from somebody else, but it worked pretty well. And there were other algorithms in there. But that was just kind of a basic.
What company was that?
That was SAIC, Science Applications.
Oh, okay.
Yeah.
We're diverging from the topic a little bit.
Yeah.
Here.
Sorry.
Yeah.
So let me just try to finish this up, because you know it was just a fun hobby project trying to figure this out.
Yeah, it looks like it.
Yeah, and I had some fun in the computer creating these figures and so on. But what I really liked is these kinds of pictures that you see. Okay, what actually happens at the focal point of a telescope if it's not quite right? I mean, if you put this thing at infinity, everything is going to be at one spot. But if you're a little bit off axis, you could use this math with a small change as well, and it would sort of look like this, I think. And I think it's just kind of interesting to see how all that comes together in the focal point. It makes you think a little bit about, it's amazing. If you look at the x-axis, this is 176.2. Well, actually, this is not the right one, but this one here, this is a real telescope. This is like 1518. That's my 1500 focal length, and you're not quite at infinity, so you've got a bit more. 0.98, and over to the right we've got 1519.08. So this is 1/100th of a millimeter that where all this stuff takes place. And then these red markers here, they're within like less than 1/100th of the width of the figure. So we're talking 1/100th of a millimeter. So that's then you're less than a micron there. It's kind of interesting how all this stuff happens.
Is this a reflector or a, is that a parabola?
Reflector, yes.
Okay.
Happened already.
It's zoomed in. And these numbers that I get, I believe that they are realistic, but it's difficult to tell how this actually relates to airy disks and interference, because that hasn't really been addressed. But it gives you an idea of how far away you can go and still be, have the wavefront be in phase. And these numbers, these are numbers that are not quite unrealistic, actually. Now this one here, this was for the case where, what was it, a 6-inch? Oh, this is a crazy example. But this one here, Niels Olof Carlin, he had a 16-inch scope, and he couldn't go farther out than a certain distance, so he had to stay close. And then you get because of the what you call it, the back focus. He had back focus limitations, so that's why this is such a large number. So. Anyway, it looks like it's okay, and I'm not quite sure if the math of Carlin is okay. He did not document anything. He just said he did a whole bunch of algebra, and this came out of it, and he presented a table. He's a smart guy, but he did use that lens formula, which I have avoided, and I think my method is more exact. So anyway, it was sure fun. That's I can forward this document if anybody is interested, but yeah.
So
That'd
is
be
this
great.
just
Push
a question?
that out to me.
I'm sorry, go ahead.
Well, I wanted to say to Henk, yeah, if you want to forward that to me, I'll see if I can make a link
I'll
to
forward
it.
to you. Yeah.
So
Okay.
is that for putting an artificial star out at a distance and then calibrating for atmospheric interference, or what? The original point. I'm sorry, I lost the original point.
Well, some people like to make sure that a telescope has a nice airy disk to see if the quality of the mirror is okay.
Okay.
You can also you collimate your scope with a laser collimator, but the final test is usually considered to be okay. If you point it at a star, is the airy disk symmetric, and is it regular, and so on.
Okay.
But you're right that in normal daytime situations, there's probably got a lot of heat in the atmosphere, and it will deteriorate but you might mostly be doing this in the dark anyway. It's not something that I've done, but there are artificial stars for sale, and there was this person asking, well, how far away do I have to put this, and what is the diameter of the pinhole, which is a question that I have not.
There was a story that Tom Whittemore told about John Dobson, and supposedly he used what was it, the eye of a crow sitting on a telephone wire or something as an artificial star. It was something really wild, but
yeah.
I don't know how exact you have to be with an artificial star. Jerry was talking about the ball bearing. You were talking about Christmas ornaments.
Yeah.
It seems that the beam of light coming back, the return is somewhat the same, isn't it?
Well, you want it to be as, for when we do Foucault testing, we would get a null test if we had a sphere. So we're using a spherical wave there. But when you look at the real star, you want a plane wave, flat wavefront coming in.
Yeah.
And that's what you're testing with spherical waves and extrapolating to how it will work when we have it out looking at an object at infinity.
And by the way, Jerry, what you were talking about was the bath interferometer. I
Yeah.
think that's
No,
nothing.
that's the one where what's his name, Mike had found some articles for. And we
Right.
were considering making it a project for our club, but we
Which
use
I've been too
different-
lazy to make.
you're too late to make- no, it's just the project that we're getting to. It's a
Yeah, we're
hostage.
gonna get to it, Mike.
Yeah, but we use different lasers in where I used to work.
You could have used a FITSU interferometer, which is
What
a
I've heard
different
before
type.
for the equivalent of a ball bearing, it was like a reflection off of an insulator on a telephone pole.
Yeah, yeah.
For a 12-inch scope, you wanted it to be something like 300 feet away or 400 feet away to get a really good reading. So
What I need to do is experiment. I've got a couple old fiber optic cable leads, actual fiber optics, and those have extremely small aperture holes. I think they're multi-mode. Single mode probably would be smaller, and with a high power LED light, you can get a reasonable brightness.
Henk, what the one question that I would have is that on what you were searching for there, if I'm right in this, is that you were trying to find the optimal distance of an artificial star to test your optics. Is that correct?
Yes, the minimum distance actually. I just wanted
Minimum.
to see when you get too close to the telescope so that your interference pattern goes to hell. So
Oh, interesting. Okay.
Yeah.
Were there anything that in your findings that would give you an idea that I know that in your scope you were what, 12 meters away?
120.
120. Okay.
Yeah. I never tried it physically, but this is what comes out of the calculations actually. So yeah.
Okay. Okay.
So the larger the scope is, the further away you have to go. So 12 inches is kind of large. For a 6-inch, it would be much closer.
What about the F ratio?
Yeah, the F ratio matters as well. So that's the constant R, right? That's related directly to the
Right.
F ratio.
And the slower the scope, the easier it's going to be to get diffraction limited.
The longer the radius of curvature?
The slower the scope, yeah, the longer or the smaller the diameter, either one.
Okay. Yeah. I'm not going to follow the math that you did, but I enjoyed. I really enjoyed watching it.
Yeah, I try to avoid it. Well, we're all sitting here at home with COVID. I had nothing better to do, so I thought, okay, well, what the heck, this is.
Well, the one formula you had that really I looked at was it was R squared over 2R, and that's where we're measuring the infinite number of points on a parabola for the depth of the curvature at any one of those points.
Yeah,
So,
that spatially spread line where all those points come together that Henk calculated, that's what we're measuring when we do the Foucault testing. And that formula you just quoted gives us the spacing between neighboring points along there, where to move the knife edge to see that particular zone of the mirror. Because the whole mirror doesn't cooperate and send it to a point like that until it gets to be about F10 or F11. And then you're back to a sphere. So everything from the light source goes right back to the light source as a perfect point. You're real fast. And I noticed your scope, the fastest case you had on there was about F.3.
Whoa.
For your calculations.
0.3.
0.3, yeah.
That's a pretty
If I interpreted the numbers right.
pretty steep dish.
Yeah, soup bowl.
Well, Mel Bartel does like f2.2 or 2.5.
Yeah.
Wow.
I can't remember where I saw the Niels Olaf Carlsen, unless it was him doing an article on Foucault testing, and he had a bunch of diagrams of whether you're moving that knife edge inside R or outside R, and how it cuts the light source off. I don't know if that was Niels Olaf Carlsen, but I remember reading something by him. Do you remember that, Jerry? That was that article on Foucault and understanding Foucault.
I've read so many articles on that. I don't remember the
Yeah, I lost you.
Mel Bartels.
Yeah.
By the way, while you were giving your presentation, I looked up Nils Olaf Carlin, and Cloudy Nights had a thing. I guess he died 3 years ago. So
Oh,
Yes,
wow.
yeah,
may he rest in peace.
yeah.
Boy, we're losing a lot of the good ones.
Yeah, I got scared because I was, like I said, I had borrowed his design for my primary mirror cell, which is just two things, okay, with the swivels. And so I went to go find it, and evidently because he had died and nobody picked it up, the web page was gone for like about 3 or 4 months, and then it came back on again. But I think what you were talking about is, it's backwards. Okay.
That's it.
David Harbour.
Oh, David Harbour. Thank you. Yeah.
Which is
okay,
not the
that's
same
Harbour.
David Harbour who did Strange Times or whatever.
Yeah, you're right.
On
Yeah.
Netflix.
Yeah, thanks. That's the one. That's pretty good
Stranger
information.
Things. Yeah.
Yeah.
You might say Stranger Things of optical design. Okay.
Upside down.
Yeah, I have the homepage of Nils Olaf that I can share, Tom, if you allow me.
Yeah, or put it in the chat. You could click on chat at the bottom and you could paste it there.
Oh, very good. Yeah, the chat box. The bottom,
Okay.
you can click on chat and you can see, and you can pass information on that way. It's a good way to go.
All right.
I
I'll
put the
do that.
Wikipedia thing on Lagrange points there.
Oh, yeah, I see it.
Yeah, make sure it says to everyone. So
So you
does.
see it?
Yeah.
Well, I'm not sharing now, right? Okay, yeah.
Yeah, you don't have to share, just chat
Yeah,
and
okay.
Yeah,
the
it's there
message.
for you.
Click on chat here from to everyone. Okay. All right.
Gotta
So
go. I have an asteroid at 2:30, so see y'all.
Hey, Chuck.
2:30.
See you, Chuck. Good to see you.
Bye, Chuck.
Bye.
Yeah, I've posted the link there.
And
By the way, Hank, I love the trig. The more the better. Bring it on. Your assignment is to get a closed form solution for an ellipse. I looked at it recently. There are guys. Well, I don't think the closed form will ever be solved, but that's maybe we talked about this in a previous thing. But that's a pretty interesting problem. So
we'll have to put
Yeah,
you in a.
there are actually several ways of getting an ellipse. Like for instance, you can take 2 points with a string between them at right angles,
yeah,
and then make hold the string at 2 places and draw the
but
Yeah.
I mean
put the pencil on the string and go all the way around, and you get a nice ellipse. And you can do the same thing with hyperbolas as well in a different way. If you look it up in Wikipedia, there's all kinds of things. Because I was thinking, well,
Yeah.
this problem, that maybe somebody else figured out already that there was some very simple way where you've got like a constant path length and the envelope turns out to be some sort of hyperbola. I looked through all the stuff that we had there, but I didn't see anything that fit my
Yeah,
presentation.
that Indian mathematician that was in the 30s or something came up with one of the best approximations. This is the path length around an ellipse, which pertains to astronomy pretty closely. And it's like
Yeah.
kind of amazed me that when I found that out that there's no solution for that. So
In the parabolas, I believe that you take the arc length or the total length between, you draw a line and then you draw a point. And where the distance between the point that you drew, the single point, which is the foci, to that any other point in space, and where it's equal to the 90-degree line to the line, those two things are equal, and that'll define the parabola.
Aha. Okay.
Hmm.
Yeah, cool.
Oh,
Where they have a constant sum, not where they're equal. And if you have it so they're a constant difference, then you get a hyperbola,
Yes.
something
Exactly.
like that.
Yeah.
But you can do the ellipse, like you said, graphically with a string and 2 nails and a piece of wood. But you can
Yeah.
also do the same thing mathematically by making the 3 arcs or the 3 lines sum a constant.
Yeah.
And that'll give you the ellipse.
I'm going to need to leave in a little bit because it's now here.
before you leave, Bob,
Yeah.
what are you still doing a lot of imaging?
Oh, yes. Yeah. Yeah. Before I think you came, Tim, I was talking about we're working on an observatory here. We're in a continuing independent living continuing care community called Westminster Village in Scottsdale. And so I'm working with them to get an observatory going. I'll be using my 11-inch scope there. So I'll be doing, continuing to do the imaging, quite a bit. And I did one of the conjunction. I don't know whether I can get that up. Before I do that, I want to, Mike, I wanted to ask you,
Yes.
I'll leave a message for you on the chat, but I really would appreciate if you might contact me via my email and just let me know some of your experiences with the dome and things to look for. You mentioned one, there may be others. So the more I can learn about that, the better. So, but I'll leave a note for you.
Bob, I'll share your conjunction there.
Oh, okay. Why don't you do that? There you go.
Nice.
Very nice.
Oh, wow. That is neat.
So is that photoshopped at all? You got one of the moons with Jupiter and you got Saturn pretty good?
Yeah, well, this was taken with the ZWO camera.
Oh, stacked.
Right up here is the camera used, and an 8-inch at f10, and it's composed of 300 images stacked, and then it's it's finished off in Photoshop Elements, and so this is the distance here is 6 minutes of an arc.
Mm-hmm.
You mean the separation between the two?
Separation, yeah. You can't, if I had to do it over again, I would have put in my focal reducer, have a little wider field of view than I got. But once I was set up with my camera, I didn't want to take time to change it all around because, things were going down quickly.
Yeah.
I had a focal reducer on my C8 when I took mine.
So anyway, that was taken from our observatory site here in where I'm living now. Yeah.
Excellent.
Nice.
So anyway, I'll join you guys another time. Do you meet monthly or weekly? How often?
Weekly, every Tuesday.
Every Tuesday. Okay.
Yeah.
Well, I will be dropping in again. So
Put it on your calendar.
yeah, I will. And I'm going to go ahead and send a note over to you, Mike, on the chat. So anyway, great. Thanks so much. It's been great to see everybody.
Yeah.
Yeah, it's good seeing you, Bob.
Great.
Bye.
So Chris, have you been doing anything interesting with your telescope?
Interesting. I could show you, and it's kind of like an aberration, but I was excited about the conjunction, and I had gotten a new finder scope for Christmas, and my wife got it for me, but it had a little 1-inch, the two holes are 1 inch apart, but the holes in my orange tube are 2 inches apart. So I was rushing, she gave it to me early, so I was rushing to figure out how to put it on there. And so I don't know, can I share it to show you?
Sure.
Will that work? Oh, it will work. Okay. Let's see, hold on. Oops, hold on. Let's see if I could show you. Because I feel like this is the opposite. This is the exact opposite end of Henk's presentation. Is that, I don't know if you could see that, but it just turns out that on a mending plate for 2x4s, when you put them on either end of the 2x4,
Yeah.
it has 1 inch holes spaced apart on one end, and then 2 inch holes spaced apart in the other end. So I was rushing in my studio, and this is the best solution I could get to before Saturn and Jupiter went down.
Yeah.
So my question for you guys was, I'm sure there's a very simple product that because it just has 2 little screws. They're kind of invisible here.
That doesn't matter. Fact is, it works. And
It
why
kind
change
of doesn't. Like, the thing that surprised me is I was halfway proud of it,
Yeah,
but
good.
I can't get the dot quite high enough. You know, I was just lining it up. It was so easy to, I was lining it up, and I could never even adjusting it to for maximum.
Chris, put a shim in the front.
Yeah.
Okay, so I left out the picture where I wadded a bunch of paper because I thought that would move past funny to the point of being sad. But that was what I did. Okay. Is there a product to just? Is there like a kind of easy to find product to just kind of?
No, it's better to get something that that the night air won't dissolve, and just kind of shim it in the front. And if it's something you have to, if you're going to be taking that off and on, then yeah, you might want to look for something a little bit more permanent. I don't have a good idea on that right now, but certainly if it's a mounting plate underneath this, you might consider maybe some type of filing of the back end.
Well, I have a suggestion. I don't know if you have a Telrad, but that's what I use. And I don't use the base of the Telrad, but just the other part. And turns out if you just plop that onto the cylinder, because it fits on there perfectly, and wrap a rubber band around it, around the whole scope and so on, it's pretty tight and it works really well. So then you can take it off and on. Yeah, it does. I tried it on my Z12. I tried it on my other scopes. It works amazingly well.
A rubber band?
Yeah, what I use is I'm a bike rider, so I have all these bicycle tubes. That's very good rubber. That rubber never dries out. It keeps it stretched. It's much better than any other rubber band.
I have these large. For drawing boards, we have these really large, very strong rubber bands. I never thought of that because I figured it would slide around because it's a cylinder.
If you have a bicycle tube that's so cheap, you can just cut it to any size you need, so that whatever.
Yeah. It just has, the I didn't take a good picture. I just ran into my studio today, but there's just a little sliding kind of slot so you could push it back and forward and back in there. So I thought there might be a ready-made product, but that was my thing. And then I was going to buy the 360. I was excited, I went out for all these days and took just some quick shots of the conjunction, and the kids loved it. So I just had a 40 millimeter and it worked out pretty well. I got pictures of it every night. And then I know you guys recommended, that was my, this guy, right? This is the one, Jerry, I kind of had lost the link. That's the one for fork mount. Okay. So I had some product questions, but I kind of thought that was a funny, that was my funny adaptation to getting gifted a new finder scope and having the wrong size thing.
Real laboratories are full of little kludge steps like that, so there's nothing dishonorable about it.
I was like, I didn't want to drill more holes because they had a camera mount, and I was like, this thing's gonna be like Swiss cheese. So that was what I came up with. But
yeah,
I had a similar problem when I have the TV 101, a 4-inch refractor, and I was using a white light filter. This was on solar eclipses, and I have the little what's the name of it? The little Coronado one. That's the individual Coronado scope, and I mounted that on.
The PST, personal solar telescope.
Yeah, the PST, and I mounted that on top of the tube of the 4-inch refractor. So I had white light, and then I had the ruby light, with that. And I mounted the two so that two people, that was during the solar eclipse that we had, that was just huge amounts of people. And I was at the museum that day. I think you guys were out at Big Box. And I tried to get the two to view the same sun. And it was much harder than I thought. These things were milled pretty good. And what I ended up doing, Chris, was doing exactly what I'm telling you about. Is I put some kind of shim on the front of it, and then just kind of shoved it in and then tightened it down. And it was close enough that we could get two people at the same time seeing, white light and then your hydrogen alpha on the other one. And it was kind of an interesting problem because it's odd. You just can't get them to line up perfectly. It's a really small adjustment.
Yeah, I thought it was me, but I just assumed.
I had a similar problem with going duplex with Losmandy plates with my C8 or my GPS, my C11 and a refractor, and I wound up having to take a Dremel with like a bit and kind of hog out the screw hole for the mounting for one of them so that you could move it back and forth.
Yep.
You know.
Yep. That's
So
that's a great way to go.
Wait,
You know,
for
you guys
depth
are
for depth or for like shifting it forward and backwards?
Or sideways. Or sideways. You
Azimuth. The elevation, what you could do is what I used was Coke can aluminum and just kind of shoved it underneath there.
Yeah.
On one, and got it to.
You need very little, right, Chris?
Yeah, I mean, I know a little bit. You know what I did was I took the mending plate and I actually hammered it. I must look like a maniac, but I was hammering it to like an anvil, like I was a blacksmith, to get the, you know, to get it to curve a bit. But you know, it doesn't want to curve; it wants to, you know. So then I would take it backwards and start, you know. So I got it relatively close, but then I had to wind up using like paper and stuff just because now it's not. Now it's kind of like a little. If you look at it head on, it's kind of like it's got a little curvature.
Oh, you might be able to find some kind of adapter for that tube. That's going to fit it really good.
Put it on a pipe and hammer it or something, or
I was just like afterwards. I was thinking like I just need to find something with an 8-inch circumference.
Yeah.
That I don't need anymore. Like a really big one of those discount cans of coffee that you get from Costco or something.
Yeah. Yeah.
Like
You mean a
or maybe
drum?
just use that, cut that up, you know, cut one of those guys up.
Or if you bend it, you know, bigger arc than you need, as you screw it down, it'll flatten out. That might be closer to what you need than, you know, even if it's too much curve. So
Yeah, I mean, I could do it right. It's at school. We actually have a lot of steel bending, you know, stuff that we could use in sculpture, which is I could do it right. It's all closed right now. And they have these beautiful big dies that you can kind of work with. So
yeah.
I thought you were going to tell me there was a $12 Celestron part that everybody already has, you know, that, you know, I can get on cloudy nights or something.
No, that would be $100 part from PaulW.
Yeah.
Exactly.
Yeah.
By the
So,
way, just
Tom, let me ask Tom something.
sorry, go ahead.
Did I send you a movie of a brief clip one time of Albert Highe working on a Dobsonian telescope?
Yeah. I've got that. Do you want to
Okay.
see that?
Yeah, if you could show it. It's only about a minute long.
Okay, let's see if I can get that.
We talked about him about 2 or 3 times ago, and Tim was referencing him, and I had this clip that we made at CalStar one day. He was testing Joe Doyle's 18-inch Dobsonian for how quickly its vibrations died away.
Oh, wow.
Hey, real quick too, before we run out of time here, because we're getting close. Henk, I wanted to ask you that the previous presentation you did where you had the Eclipse source code for that RA deck thing, I was going to ask you, I don't know if you said that's on GitHub or do you just have that personally, or?
I have a local repository. I don't have it in GitHub.
Is there a way to just save the whole project? I'd be interested in getting that. I don't know if that's okay.
Well, okay. So I still have that Eclipse code, and I talked about this in the OnStep group if they were interested in switching from the Arduino.ino language, which is some sort of simplified form of C++, to actual C++. And the big kahuna said no. So, I mean, he never got into the discussion, but I guess the guy was annoyed or something like that. I mean, it's just one guy who writes the code, right? And
yeah,
so
basically it's been the C++. We had this thing when we were doing the actual experimental satellites. The C was more compact and runs faster and like that. I mean, you got a lot more possibilities with C++, but
yeah. Well, so my problem with it is that in Eclipse you have a very good browser, and that's really useful if you want to understand code and maintain it. And this guy doesn't like Eclipse, or he doesn't like C++ or whatever. He just wants to keep using his Arduino interface, and he just wants to be the only person who actually changes the code. And so, well, I mean, it's great that he makes it all available. It's a really good product. So
yeah.
He has the right to do it. I have no problems with that. It's just a shame.
Yeah.
But if you want the code, then the best. So do you really want C++ code, or what do you want the Arduino code? Because the Arduino code is available on the OnStep group.
Oh, okay.
That is
Actually,
maintained.
I'll email you separate from this because I've taken up too much time. These guys want to talk, but I have your email. I'll email you separately and we'll talk about it.
Sure, yeah.
Okay, thanks.
Okay.
So Jerry, there it is.
Okay. It's not as smooth as it was on my machine. Maybe it lost something in the translation, and there's sound.
You got to go to 6 people.
Yeah. So he has a little motion sensor, I think an accelerometer he mounted in the eyepiece hole, and he's tapping it. We were kidding about that being a calibrated tap. And because he's doing all sorts of different, he went around at CalStar, there were probably 100 different sites, and he's going around because every scope that you could buy is represented there. So he was looking at the mechanical properties of all these different products.
Oh, that's Joe Doyle. Yeah.
Yeah, that's Joe Doyle.
Yeah,
That's Joe Doyle's scope there.
and that's Albert Highe in the foreground.
Yeah. There's Paul Wynn walking up.
Oh yeah.
Oh, yeah.
Ah,
Oh, is that the 18-inch scope that was available at some point in time? Because I think I actually called Paul Wynn about it to.
No, that's Joe
Yes.
Doyle's.
Oh, okay, okay, yeah,
That's an Obsession, at Obsession 18.
right. So the one that was up for sale by Paul Wynn was an Obsession 18. This was several years ago, and I called him about it.
Oh,
It might have been this one.
I think that was somewhere down in Santa Paula or something.
Oh, okay.
Is that a bag covering the secondary mirror for some reason?
Yes, it is. It's a Chivas Regal purple bag, if you know that kind of liquor.
I do. That's what made me think of it. It's just he's just protecting it during when he's not using
Yeah.
it.
Yeah, they're not, and you see the main mirror covers on there. They're just looking at the mechanical properties,
Yeah.
its stiffness. There's no optics going on.
So it's really just about the trusses and the assembly.
Yeah. He's trying to make things as lightweight as possible and as easy, as few parts as possible. And he published this book shortly after this on making telescopes using tension strings and fewer struts.
yeah. As an engineer, he really went into the what kind of trusses, what size of trusses, how many of trusses you would
Yeah.
need to make them stable enough. It wasn't until after I started really getting into this that I noticed my 10-inch Dob when I slewed it down, when I went from zenith down to like 30 degrees. If I had the laser in it, you could just watch that laser walk on the mirror.
Yeah.
There's quite a bit of movement. It could stand some better aluminum in there.
Mhm.
When I got the aluminum for my 10-inch, it was kind of, I think it's called MD. It's the stuff you get at like a regular hardware
Thanks,
store.
Tom.
It wasn't 6061, so it's not very good aluminum. Yeah, he's quite a guy. He just he won't grind a mirror, but he'll take a mirror and put it in a
Yeah.
fabulous scope. As you
Yeah,
can
he's a
see him in that.
mechanical engineer. So, but this was probably 5 years ago, so he's declining from his MS that he's got.
Oh, he's gotten worse.
Yeah, he stopped coming to the CalStars.
Yeah.
Okay, we're getting close to the end. Henk had a couple more things, but I guess I'll wait until next episode, perhaps, Henk.
Yeah, it's some old stuff, but it's kind of fun. Something about polar alignment and the method that I use. That's a short, quick one in 5 minutes. The other one is old stuff of the barn door for my 10-inch Dobsonian, which was a
Okay.
crazy project, but actually
So
real
those
fun.
telescopes you showed, Hank, 16-inch and stuff, were those Newtonians or Dobbs or catadioptric?
So the ones in the article, you mean, in the presentation, or?
Yeah, the one in your presentation.
Oh,
12 and a
those were
half.
just, so two of them were the examples from Niels Olaf, and the first one was my own telescope. So there's three, and those are all Dobsonians,
Okay.
Newtonians at least. It's about parabolic mirrors, right?
Yeah.
So that's the only thing that matters actually. And the last one was just a fictitious scope that make for good, pretty pictures, clear pictures. By the way, I'm going to work on my Dobsonian as well, because I have converted it from a Z12 with a solid tube to a collapsible, but I don't like the mechanism. It still takes up too much space in my car. I got some aluminum trusses that I want to attach to the telescope. So one of these days I'll start doing that. And I think I'm just going to do it with 6 wing nuts, and I'll just take them off, put them back on each time. It's not too much work. That way I can just totally separate everything, and I think it's going to be more compact for traveling.
Okay.
Let me finish with a picture that the Baron Ron Heron sent of his. He got a conjunction photo that someone got, and where Jupiter and Saturn got really close for this person, and so this is what they saw. Can you see Saturn here?
Yeah.
Yeah, that's a close pass.
Yeah.
Now I get it.
Yeah. Jupiter got really close.
Yep.
All right.
Thank you.
Okay,
Tom.
folks.
All
Until
right.
we
Good
meet
night,
again.
folks. Good
Thanks, Tom.
meeting.
Nice to see you all.
Bye-bye.
Do it again next week.
Bye.
Bye.
All
Don't
right.
get any
everyone.
no COVID. No COVID.
No COVID.
Wear those masks. Stay away from people. All right. In meeting. See you guys.
Okay, thanks.